Alright, so in the last video we looked at solving for the axial force, shear, and moment as a function along the length using what we call the equilibrium method. Now, as an engineering spy, a lot of times you have to rely upon the contacts that you make in the field. And that means knowing how to negotiate relationships with those contacts. Well, it's the same thing for beams. We can always rely on equilibrium. But sometimes we can leverage the relationship, such as the relationship between shear and moment, in order to use a different method to solve for these axial force, shear, and bending moment diagrams. And so that's going to be what we call the method of integration. So go ahead and take a look at this relationship and then solve an example using it. Remember, there's a lot of crazy load functions out there that we need to handle, so method of integration is going to be your friend.
Alright, so on to the third method, axial force, shear, and moment diagrams as a function, but using the method of integration. Now, we really don't have too much to do with axial force. We've already handled axial forces in this class, so I'm going to focus in here on shear and moment. So we're going to look at this arbitrary piece, and we pulled this little block out, and I'm going to draw the axial force, shear, and moment on the block. Now, going from the left-hand side to the right-hand side, we need to also, because we're making a cut on both sides, put in our positive axial force, shear, and bending moment on the right-hand side as well. However, they don't have the same values. They have some differential value, because this is a differential value of length dx, and so our values all change by some differential value. So I have that expressed on the right-hand side of my cut. Now, to come up with the relationship between shear and load and between moment and shear, I'm just going to do equilibrium on this little differential element. So if I sum force in the x direction, I see that I have negative n plus dn. And I'll put those in parentheses, and that equals 0. So if I do some cancellation, that basically tells me dn equals 0. And what that really means is that the transverse load, so this transverse load function, omega x, doesn't really change anything about my axial forces. And so I see that really the only thing that omega x has a contribution to is the change in shear and then also the change in moment. So to come up with how the load relates to shear, I'm going to sum force in the y direction. Here I have V on the left-hand side minus the quantity V plus dV on the right-hand side. And then I also have to subtract out my omega x function. And so that's going to be the function, and then like a resultant load, I need to multiply by the distance over which it acts, or dx in this case. So just writing all this out and putting my negative signs through, I'll see that v and v will cancel with each other. And so basically I can write an expression for dv in terms of dx. I can show that dv dx equals negative omega x. And that's going to be a key relationship. That tells me that the derivative of shear equals negative omega x. I'm going to do the same. My third equilibrium equation is to sum moments, and I need to pick a point, so I'm going to pick point O in this case. Summing my moments about point O gives me m plus dn minus m on the other side. Let's see, my axial force and shear cancels out except for my shear on the left-hand side. So that gives me a minus v times the distance of dx. And then I have to account for the resultant force again. So that's omega x dx. And that's going to act at a distance of dx over 2 relative to point O. And so I go through and set that equal to 0. Bring my signs through. Alright, so I can see quickly m and m will cancel. Now I have this dx squared over 2 term. And basically we're going to say that this goes to 0. And this is pretty much true. Dx is a differential element, so it's already very small. So dx squared is incredibly small. It's going to be orders of magnitude smaller than our deflection. So as long as we take a small differential element and our beam is undergoing relatively small deflections, which we'll learn a little bit more about what we consider small deflections in a few more lessons, we're going to assume this term is negligible. And so basically that then says that I can write an expression that says that dm dx equals v. So the derivative of moment is equal to my shear, and more generally v of x. If you want to put v of x, or if you don't want to put v of x, it's okay. But basically the derivative of moment is going to be shear, and this is another important value. All right, so how do we use method of integration to solve some problems? So like any good spy, we drop back into our standard book of procedures and see what we want to do. So if we take a look at the procedure at the bottom of this page, we'll see that step 1, we compute some reactions if necessary. Second, we determine a function for omega x. Thirdly, we integrate for v of x. From that expression we derived above, we can see that v of x is going to equal the integral of negative omega x. And likewise, we can write a value m of x we'll see is going to be the integral of v of x. And so we learned this relationship hopefully in statics. If not, this is a good refresher, and we're going to use it to much success in this following problem. So in example 3, we have a parabolic spandrel, and now, this is just another load, so don't freak out about it. But a lot of times we have some different loads on our beams, and we just have to learn to be comfortable handling whatever loads those happen to be. Now, this load, this parabolic spandrel, can be generalized as omega x. And that's going to be one of the things we need in order to solve this problem. We need to come up with a function, because we're going to integrate, and our starting point is going to be with omega of x. And so we're going to need to determine what omega of x is. Now, you can go back to trigonometry, pre-calculus, wherever you learned how to come up with parabolic functions, right? So this is a parabola. If you want to talk about the apex and the curvature, go ahead. I basically like to take what we call like a boundary value approach, kind of a general approach. So I'm going to say omega of 0 is 0, and omega of 10 is 0.6. And then the last thing I have defined there is my slope is 0 at x equals 0. So that means omega prime of x, or omega prime at 0, has to also be 0. Now I know that this is a parabola, so very generally I can say omega of x is equal to ax squared plus bx plus c, right? Where a, b, and c are constants that I don't quite know yet. But I have 3 conditions above that I've defined, so I'll be able to solve for these 3 constants. So I start with the first condition, omega 0, and I plug in a 0 squared plus b times 0 plus c equals 0. And so that basically says that the little constant c has to be 0. Next, I'm going to do omega prime, and this, just take the derivative. This is going to give you 2ax, or 2a times 0 plus b. C obviously goes away because it was 0. And this shows now that my constant b is 0. And lastly, I'll do omega 10 equals, and I plug that in, a times 10 squared. Now remember, b and c are 0, so they go away. So this is just equal to 0.6. I solve for a, 0.6 divided by 100, or 0.006. And so without diving too hardly into parabolic equations and pre-calculus, I figured out that omega x has to be 0.00x squared. And you can test this out. Plug in 0, it's 0. Plug in 10, you get 0.6. So I'm pretty confident that this is going to be our equation for the spandrel. All right, that was just kind of a good throwback to, our math classes. So now we're going to integrate, and this is just going to be like Calculus 1 all over again. If we take a look at our procedure, we need to compute the reactions if necessary. That was step number 1. I would argue in this case we don't necessarily even need to calculate these reactions. From status class, we would kind of struggle to figure out how to calculate these reactions. But we'll see that if we kind of leave things general, we might be able to figure out what these reactions are in the end. So AY and BY are kind of unknown at the moment and not easily found. AX is 0 because there's no horizontal forces. But I'm going to move on to step 2. So step 2 is to determine a function for omega of x. We did that above. So omega of x was 0.006 x squared. All right, so that was, again, necessary to solve this problem. We'll move on to step 3. Step 3, we're going to solve for v of x by using the relationship between v of x and omega x. So that relationship from the previous page was that dv dx equals negative omega of x, or in this case, it equals negative 0.006 x squared. Now I'll integrate both sides of this equation. I integrate dv dx, that's going to give me v. And if I integrate the other side with respect to x, I get negative 0.006 x cubed divided by 3 plus some constant, and I'll call that constant of integration C1. Now, I don't really know anything about my shear at this point, so I really can't solve for C1 yet. So I'm just going to leave it here. This is good practice for when we do, like we're in a couple lessons, we're going to do bending deflections, and sometimes we need to just leave these constants be and solve for them later. So I'm going to move on to step 4 and to integrate for the moment. So from our previous relationship, we said dm dx was equal to v of x. And now we'll say, well, we have a function for v of x, so that was minus 0.006 over 3 times x cubed plus c1. Now, again, I'll integrate both sides. Integrating both sides gives me m of x. That's going to give me minus 0.006 over 3 times 4 now. And now that gives me x to the 4th plus c1 times x plus a new constant of integration, c2. All right, so I now have values for v of x and m of x. That was our main goal. But I have these constants that I have to figure out still. And so I have to look at my beam and figure out what do I know. And we're going to call these boundary conditions. What do I know in this problem? And we'll look at this more in the future classes. But I know that at a pin and a roller, as long as it coincides with the end of the beam, I know my moments have to be 0 at those locations. So basically m of 0, so m at x equals 0, m of 0 has to be 0, and that just tells me that the moment at A has to be 0. And likewise, the moment at 10 feet, m of 10 has to be 0, because the moment at B also has to be 0. And so now I'm going to use these boundary conditions, and I'm going to substitute them into my moment equation that I underlined there in black. So starting with the first one, m of 0, I plug in m of 0, and I basically get 0 plus 0 plus c2 has to equal 0. And that tells me in second constant of integration c2 is 0. Next I do m of 10. So now I'm going to plug in m of 10. That gives me minus 0.006 over 12 times 10 to the 4th plus c1 times 10 equals 0, because c2 was 0. And now I solve for c1, just do some algebra. c1 turns out to be a positive 0.5. And so now that I have these two integration constants defined, I can go ahead and I can write final equations for both my shear and my moment, because now that I know what these constants are. So let me go ahead and do that. M of x in the end, doing some math, is going to be minus 0.0005 x to the 4th plus 0.5 times x. And I'll squeeze it in here for shear. Shear of x is going to be minus 0.002 x cubed plus 0.5. And finally, our goal was to plot this along the length for all these forces, so that we can know what the maximum and minimum are at any point along the length. So here we go. I plug in v of 0. V of 0 gives me 0.5. V of 10 gives me negative 1.5. If I plug in 10 into my v of x equation, I would get negative 1.5. And it's a cubic function between them. It looks something like this. I add my positive and negative shear sign convention elements, and I'm complete. I'll plot m of x next. M of x is going to be a x to the 4th function. If I want to know where the maximum or minimum occurs on the moment function, I can look to where my shear is equal to 0, because wherever the derivative equals 0, that is a max or min. That's a calculus thing. And so since the derivative of moment is shear, then I know that where shear is 0, moment is a max or min. In this case, it's a max. I get some sort of quartic function in there, and sketch it in. I'll put in, this is the max. You could figure out, you could solve the v of x equation to solve for the x. Set v of x equal to 0, solve for x, and plug that in. You could get that value. But that pretty much sums up how to use method of integration.